This meeting is being recorded.
Oh, hello, Venkata. So, can you all hear me?
Hey, Tom. Hello, everyone.
Hey, Venkata. So, can you hear me okay?
Yep.
Okay. We've started the recording, and let's go ahead and get started. And I prepared the slides? Did anyone want to pick up after me, or I want to introduce Professor Galton, but do any of you want to do the intermediary slides, or I'll just take it?
Yeah, sure. Whatever is comfortable. Yeah.
Okay, I think we'll just go. I'll take it. Welcome to the MTT Santa Clara Valley, San Francisco section, March 22, 2022 Virtual Tech Talk. The title, topic today is Spectral Breathing and its Mitigation in Digital Fractional-N PLLs by Professor Galton. We're really lucky to have Professor Galton of the University of California, San Diego, who has a lot of experience in practical matters in these systems, which help us take advantage of mixed signal and digital techniques for communication systems. So we'll be talking about a few notes about the meeting, COVID-19 update. I'll introduce the officers. I want to comment about IMS in Denver. It's going to be a really exciting conference. And then we'll introduce the speaker and the talk. And then there'll be a Q&A period. And Ian, sometimes what we like to do is pause at logical points to see if there are any questions. That way people don't get too far behind you. But it's up to you how you'd like to take the Q&A.
I'm happy to do that, and I'm happy for people to jump in. One thing I'd prefer people not do, though, is to send me chat messages, because it's just really hard for me to keep track of those and keep track of my own talk.
Right. I think with the size of in this, we'll explain how you need to ask a question. So this meeting is being recorded, and we are live on Zoom. Links to the recorded video and the slides will be sent to all registrants. Please don't attempt to turn on your camera, and your mics will be muted. And when you want to ask a question, please use the raise hand reaction button, and then the host or co-host will unmute you and you can ask your question. Please ensure that your Zoom, the display name in Zoom matches the one you used to register. We need to check you in to enable the reporting that we do to the all volunteer organization that we are, into the IEEE, showing the interest you've shown in our talks. All in-person meetings related to our chapter are canceled. Normally we meet in person, but everything's online webinar until further notice. We're working on changing the scene on that, and we're hoping to go hybrid in May. So my name is Tom McKay. I'm the chair this year. Our vice chair is Venkata Gade. Our secretary is Darren Phelps, and Tan Tu is the treasurer. The IEEE is an awesome professional organization. I've been a member since the early 80s, I suppose. And it really is the place where technology for humanity is advanced, in my view. And we do this through highly cited publications, conferences, technology standards, and professional educational activities. And our society, actually, it's had a name change. It's the Microwave Theory and Technology Society, and we forgot to update that. But we focus on radio frequency, guided, wave, and wireless technologies. And you can join by clicking or going to these places on the web, or this LinkedIn is our hashtag. IMS is in person and registration is open. It goes from the 19th of June to the 24th of June, and is in Denver at the Denver Convention Center. Early bird registration ends on May 12th. I highly recommend you register. Okay. Spectral breathing and its mitigation in digital fractional-N PLLs. Let me introduce Professor Galton. One second. Sorry. I'm sorry. Where is it? Yeah, I'm having Google problems. Okay.
Slide 8.
No, I know the slide. I had something else.
You want slideshow?
No. There it is. I have a cheat sheet. Yeah. So sorry. So Ian Galton is electrical engineering professor at the University of California, San Diego, where he teaches and conducts research in mixed signal integrated circuits and systems for communications. His research involves the invention, analysis, and integrated circuit implementation of critical communication system blocks, such as data converters and phase lock loops. Prior to joining UCSD in 1996, he was with the University of California, Irvine, and prior to 1989, he was with AccuSong and Mead Data Central. He received a BS in Science, Bachelor of Science from Brown University in 1984, the MS and PhD degrees from the California Institute of Technology in 1989 and 1992, all in electrical engineering. Dr. Galton has served on a corporate board of directors and on several corporate technical advisory boards. Ian served as editor-in-chief of the IEEE Transactions on Circuits and Systems, Analog and Digital Signal Processing, and on the administrative committee of the Solid State Circuit Society. As technical program committee member, and also as technical program committee member for the International Solid State Circuits Conference, which is currently still going on virtually. He is a distinguished lecturer of this year's, anyway. He's a distinguished lecturer for the IEEE Solid State Circuit Society. Dr. Galton is a fellow, IEEE fellow, holds the UCSD Skyworks Endowed Chair in High Performance Communications Devices and Circuits, and he received multiple Best Paper Awards from the IEEE and the UCSD Electrical and Computer Engineering Department Best Teacher Awards. Now, although digital phase lock loops offer several advantages over their analog counterparts, they suffer from a major disadvantage that is rarely disclosed in published articles. The disadvantage, known by those experienced with these systems, is known as spectral breathing. It's caused by component mismatches among the frequency control elements within a PLL's digitally controlled oscillator. The mismatches introduce DCO frequency modulation nonlinearity, which fluctuates and therefore causes erratic variations in the PLL's measured phase noise spectrum as the DCO's free-running frequency drifts. This phenomenon called spectral breathing because the measured phase noise spectrum tends to slowly swell and contract over time as if it is taking breaths. During these breaths, the PLL phase noise often becomes severely degraded. This talk will present a brief overview of digital fractional-N PLLs, a detailed explanation of the spectral breathing phenomenon, and an experimental demonstration of and solution to the spectral breathing phenomenon in the context of a recently published digital fractional-N PLL IC. This demonstrated solution is a multirate dynamic element matching technique with a mismatch noise cancellation technique that together eliminate spectral breathing. So, Professor Galton.
Okay. Well, thank you very much, Tom. Let me share my slides and we'll get going. Okay, so I assume everyone can see my slides and in the presenter.
Not yet.
Oh, hold on.
Yeah, that's better.
Okay, that was strange. All right, so so thank you for the introduction, and you've already said the title, so I'll skip this page. So as Tom mentioned, I'm going to talk about a number of things related to spectral breathing. I'm assuming that people are somewhat familiar with analog fractional-N PLLs. So I'm going to use them to launch into a brief discussion of digital fractional-N PLLs. And then I'm going to go to the problem of how do you control the frequency in a digitally controlled oscillator, and where that leads to the spectral breathing problem, and then ways to mitigate spectral breathing. And then the approach that I'm going to talk about in detail, this combination of multi-rate dynamic element matching and mismatched noise cancellation, and then measurement results from a PLL IC. So, and as we talked about, please feel free to interrupt at any time with questions. It's very dull to sit in front of a computer and talk to my computer for an hour. So I actually would welcome the break of people asking questions. Anyway, so let's first talk about digital fractional-N PLLs at a very high level. So in order to do that, I've got to start somewhere. And since a lot of people are already familiar with analog fractional-N PLLs, I thought I'd remind you of what an analog fractional-N PLL is, and then explain how we can morph that into a digital fractional-N PLL, and why you might or might not want to do that. So this is a classic analog fractional-N phase lock loop. It's got a voltage controlled oscillator, a multimodulus divider with a integer value n, and a fractional part that's represented as the output of a delta sigma modulator. So the fractional value is alpha, and it's quantized to integer values and added to n. And the divider output is compared against the reference with a phase frequency detector, a charge pump, and that controls an analog loop filter. So the objective here is to generate an output frequency, which is n plus alpha times the reference frequency, where n, as I mentioned, is an integer, and alpha is a fractional value. And typically between either 0 and 1, or minus 0.5 and 0.5. So this is just a very simplified timing diagram. If the reference edge comes before the divider edge, that means that we want to speed up the VCO. And so the PFD and charge pump work together to create a pulse of current with a width that's equal to the difference between the VREF and VDIV edges and an amplitude of I. And if it's the other way around, if the divider edge comes before the reference edge, then we do the opposite. We put in a negative pulse of current into the analog loop filter. So, and these square waves look like they're idealized, but actually in phase lock loops, we want these edges to be as abrupt as possible, because that minimizes the conversion of amplitude noise to phase noise. So we actually do try to make these edges as abrupt as possible. Anyway, so if we think of everything in this gray box as a phase error to current converter, then you can think of the general form of an analog fractional-N phase lock loop as a phase error to current converter, an analog loop filter, and a voltage controlled oscillator, all driven by a reference oscillator. And this is sort of the vanilla version. There are all kinds of tweaks and enhancements you can do, but they all have ultimately have this general form shown below. And so there are pros and cons to analog fractional-N PLLs. And they relate ultimately, well, to a lot of things, but importantly to phase error. So we want high performance, which means in the context of a PLL, low phase error. And by phase error, I mean phase noise and spurious tones. So phase noise is the phase error minus the spurious tones, which are inevitably there. And phase error is the phase noise and the spurs that show up in the phase error spectrum. So the pros are that we have the lowest phase noise and spurs reported to date in analog fractional-N PLLs. So in mobile phones, for instance, the high-end mobile phone chipsets inevitably use analog PLLs. They're based on standard, well-understood techniques, but they have some cons. They usually require very large loop filters. They're on-chip loop filters, but they're very large, so they're expensive, and they're not amenable to digital enhancement techniques. Like if you have digital signal processing inside your loop, there are all kinds of tricks you can do, some of which I'll show you in this lecture, to improve performance. But if it's all analog, it's much harder to do that. And then we're sensitive to charge pump nonlinearity and leakage. So the green happy faces are the pros, and the red sad faces are the cons. So that's a super fast reminder of what an analog Fractional-N phase lock loop does. So now let's talk about the relationship between analog and digital PLLs. So during the nth reference period in an analog PLL, the charge pump current pulse is proportional to the phase error, because ultimately we're trying to measure the phase error at the output of the PLL and adjust the input of the VCO to reduce that phase error. So ultimately, each pulse of current from the charge pump is a measure of the phase error plus stuff we don't want. And the stuff we don't want is mostly quantization error, because when we do the multi-modulus divider driven by a delta signal modulator, we're injecting a large amount of quantization error. And it's inevitable. There's really no way around that. I mean, there are ways to subtract out the phase error, do quantization noise cancellation and things like that. But ultimately, we have this large amount of quantization error there. And so a reasonable question is to say, well, or to ask, well, why, if we've got a lot of quantization error there anyway, why not just digitize the phase error and then use a digital loop filter and a digitally controlled oscillator? And so the general form of a digital phase lock loop is shown here. We've got, instead of a phase error to current converter, we've got a phase error to digital converter. And instead of an analog loop filter, we've got a digital loop filter clocked at the reference frequency. And then instead of a voltage controlled oscillator, we've got a digitally controlled oscillator. Now, the digital PLLs have been really hot lately for the last several years. And I think they've been oversold to an extent, but they're getting better and better, and they have a lot of very important uses. They're still not quite as good as the best analog PLLs, but they're getting there, and they probably will get there within the next few years. But I'm calling the slide The Good, the Bad, and the Ugly after this famous film that Clint Eastwood was in. And the good in this case is that there's no charge pump or analog loop filter, and that makes it very compatible with highly scaled CMOS technology, gives us very low error area. The digital loop filter is tiny in the case of a digital PLL, and it's enormous in the case of an analog PLL. And it's amenable to all digital background calibration algorithms. And I'll show you one such algorithm today. But the bad is, as I mentioned, they've got worse performance, at least currently, than the best analog PLLs, at least until recently. They've got higher phase noise and or larger spurs in most cases. The counterexamples that do exist, and in the back of the slides, I have just a few references. And so this one is the first reference in the back of the slides. So counterexamples exist, for example, reference 1, but they use extensive analog assistance. So at some point, you can call it a digital PLL, but if there's a ton of analog in there, maybe you might as well have just built an analog PLL. And the ugly, which is to me very disturbing, is misleading terminology in the literature. So you might have seen papers, hundreds of papers actually, that call them all digital PLLs. That's total marketing hype. Of these 3 blocks, only one of them is all digital. That's the digital loop filter. The phase error to digital converter inevitably contains analog. The DCO inevitably contains analog, and of course the reference oscillator does too. So it's completely wrong to call them all digital. And some papers call them spur-free, which is also not true. No PLL is spur-free. So PLLs always have spurious tones. So it's simply not true to call them spur-free. And I get a kick out of, if you look at some of the early spur-free papers, papers that were titled spur-free PLLs, that the same group the next year would come along and talk about how to reduce spurs. And it's like, well, if you had a spur-free PLL before, why do you need to reduce the spurs? And the answer is because they didn't have a spur-free PLL before. So I claim this is fake news. So that's my super fast overview of digital PLLs. And I'm now going to shift gears and talk about the digitally controlled oscillator frequency control problem. So again, this is the general form of a digital fractional-N phase lock loop. And we're going to focus on the digitally controlled oscillator. So first, let me tell you ideally what we'd like it to do in the context of a 16-bit input. So let's call our 16-bit input, digital input, D of N. And the LSB of D of N, where N is the reference index. So reference period 1, reference period 2, and so on. Anyway, the LSB of D of N, we want to be very small. Like we want it to correspond to a frequency change of, for example, 100 hertz. And the output frequency, the output signal, ideally has a fundamental that's a sine wave, where there's some center frequency. We'll call it FC, and then added to that is the tuned value controlled by D of N. So if we look at F tune versus time, ideally we'd have frequency values corresponding to D of N multiplied by the minimum steps, delta, which in this example would be 100 hertz. So this is what we want. And one way we could in principle do it is shown here. So here we've got our 16-bit input. I'm sticking with this 16-bit example throughout the talk. And so this is a simplified circuit diagram of a LC digitally controlled oscillator. And this reference frequency rate, frequency control element bank, ideally you could make as a set of frequency control elements that were weighted with a step size of delta, and then 2 delta, and 4 delta, and 8 delta, and 16 delta, and so on. And each frequency control element has a 1-bit input, and it essentially just adjusts the tank capacitance up or down by a small amount based on the state of the input bit. And so here are just 2 different ways that you can do the frequency control element. So each one of these little white guys is either one of these or something similar that changes the tank capacitance up or down by a step. And that step is controlled by the input bit. So I'm going to, just to give a little bit more context, I'm going to dive into some details about this guy. So, oops. All right. So by this circuit, what I mean is something that looks more like this. So it's got the MOSFET switch with some charge cancellation transistors, but the 1-bit input is clocked, and then it controls this switch. And you can show, if you just do a quick analysis, you can show that when you open and close this bit, you change the capacitance by a step, C delta F, which is delta squared over 4C plus 2 delta. So if C is 4 femtofarads and delta is 0.75 femtofarads, just as an example, that would give you a step of 32 attofarads. And what's kind of cool about this technique is it allows us to synthesize smaller capacitors than are physically realizable. Now, there are many ways to do this, but one of the nice things about this way of doing it is that the matching accuracy, if you have a bunch of these guys, scales as if it were a physical capacitor. Other methods of making capacitances that are smaller than you could physically implement typically have much worse matching, or they end up having worse Q, dequeuing the tank of the oscillator. So this is a nice approach. We use it a lot, and it's starting to be used in a number of commercial products too. The drawback, though, is that even though 32 attofarads sounds tiny, and it is, of course, it's much more than we need in many cases. We would like to have it be much, much smaller. So that leads to why the ideal DCO control often isn't practical. So the smallest frequency control elements typically have a delta min, a minimum step size of on the order of tens of kilohertz. Whereas, and by the way, I won't be able to see if people raise their hands very easily. So feel free just to interrupt and jump in with questions.
Ian, we could just check and see if Tan or Venkata, are you able to see when hands are being raised? I'm not able to.
Yeah, we will know when someone.
Okay.
Someone
yeah. So Ian, if folks can raise their hand, and then Venkata or we'll call on you, and then allow that person to speak.
So just jump in anytime. That's okay. Fine. Thanks. So anyway, the tens of kilohertz is in a multi-gigahertz LC oscillator is about the best you can do using these FCEs. And we often want, hold on a second. We often want frequency steps on the order of 100 hertz. And so what that means is we can't implement these small step frequency control elements directly. So for example, if 2 to the 8th times, say 100 hertz, is the minimum step we can actually physically implement, that means that none of these red guys can be fabricated. And so obviously that's a problem. So again, the problem is that these red guys in this example are not physically realizable. So there's a standard solution that's been around since like the early 2000s, and it's used all the time. And the idea is to take your 16 bits and break it into an integer part and a fractional part. So in this case, we've got 8 integer bits and we've got 8 fractional bits. And what we mean by fractional is any bit that's fractional, it means that it would ideally go to one of those red unrealizable frequency control elements. But since we can't realize them, what we do is we take the fractional bits and we oversample them with a delta sigma modulator, in this case, a second order delta sigma modulator. And then we go through a dynamic element matching encoder. I'll tell you what that does shortly, if you don't already know. And then it goes into a set of frequency control elements that are pegged at the minimum size, the minimum realizable size. But these guys are clocked at a higher rate than the reference. So typically they'd be clocked at something like, for example, the PLL output frequency divided by 4 or divided by 8. So these FREF rate integer bank frequency control elements, each of which is driven by one of the 8 MSBs, is essentially updating at the reference frequency, whereas the yellow ones that are driven ultimately by the delta sigma modulator are updated at this higher frequency, which is often on the order of 1 or more gigahertz. So these guys are clocking at a high rate. So the DCO suppresses the delta sigma modulator's high frequency quantization noise because the DCO has a frequency modulation to phase noise conversion. So it performs an integration. Excuse me. And that tends to suppress the high frequency quantization noise as long as F fast is fast enough. And mismatches among these frequency control elements would tend to cause nonlinearity, which would fold out of band quantization noise back in band. But we use a dynamic element matching encoder to cause that mismatch noise to also be shaped to high frequencies. And I'll explain very briefly how we do that in the next slide. But anyway, that prevents the mismatches and the associated nonlinearity from folding high pass quantization noise down into the region where the where it's not filtered out by the DCO. And one nice thing about this approach is that only 4 frequency control elements in this example and minimal logic are clocked at the 1 gigahertz or higher clock rate, whereas the other stuff is clocked at a lower rate. And so not only is that good for power consumption, but you want to minimize the number of high-speed lines routed into the DCO. And so the fewer high-speed lines we can route in there, the better. Okay, so I'm going to give you a very simple and brief overview of dynamic element matching. So dynamic element matching is used in D to A converters a lot. And so I'm just going to show dynamic element matching in the context of a D to A converter. If you think about it, the structure we've got here, it's like a digital to analog converter, but instead of converting from digital input to, say, an analog voltage at the output, we're converting a digital input into a frequency change. But it's a little easier to see in the context of a digital to analog converter. So let's suppose we've got a digital to analog converter that consists of 4 parallel 1-bit digital to analog converters. And each 1-bit digital to analog converter ideally has a step size of delta. And when the input bit is 0, we would like it to be minus delta at the output. And when the input is 1, we'd like it to be plus delta. But because of mismatches, we have these unknown errors, EL for low, K, because it's the kth 1-bit DAC, and EH for high, K, again, because it's the kth 1-bit DAC. So if I plot the output as a function of the input, so the input is going to be, when I'm done with the slide, will be labeled as X of N. When the input is a minus 2 delta, and so what I mean by this is when the input is the digital code corresponding to an ideal output of minus 2 delta, the DEM encoder has to put all of its inputs to 0, because that's the only way that in the absence of mismatches, you'll get an output of minus 2 delta, because it's minus delta over 2 plus minus delta over 2 plus minus delta over 2 plus minus delta over 2. So ideally, for an input of minus 2 delta, you get an output of minus 2 delta. But because of these mismatches, you'll be a little bit off from where you want it to be. Now, if the input, the desired output, if the input is the code corresponding to a desired output of minus delta, here, we want one of the 1-bit DAC inputs to be high and the rest to be low, because plus delta over 2 minus 3 delta over 2 is minus delta, which is what we want. But now we have some flexibility. We don't care which one is on in the absence of mismatches, which input is high. So it could be this one, or it could be this one, or it could be this one, or it could be this one. And so what that means is there are 4 different possibilities every time the input is minus delta. So what the DEM encoder does is, in this case, if the input code is minus delta, it'll flip a 4-sided coin. And based on the result, it will pick one of these red dots. It doesn't know where they are. It doesn't know what the error is, but it will pick one of them corresponding to the outcome of that 4-headed coin flip. And now if the input's 0, we want half of the inputs to be high and half low. And so there are several ways you can do that, and so on. And so for each of the middle 3 inputs, minus delta, 0, and plus delta, the DEM encoder gets to choose every time the input is, for example, 0, it gets to choose one of these red dots. Every time it's minus delta, it gets to choose one of these red dots, and so on. And so what the DEM encoder does is it selects which of those red dots among the possible values randomly and with equal probability. And you can show that no matter what these errors are, the average of these red dots will always lie on a straight line that connects the outer 2 points. And so on average, we get perfect linearity. And what's even more surprising is we can make the noise correlated to achieve high pass spectral shaping. So even though we don't know what the mismatches are, and even though the error is added after the algorithm, after the DEM encoder, and therefore the DEM encoder's algorithm doesn't know anything about the mismatches, nevertheless, it can cause the error from these mismatches to be such that we have perfect linearity plus noise, and that noise is high pass shape. So if you're not familiar with DEM, you're just gonna have to take my word for it. This is a whole course in and of itself, but at least hopefully this will give you the flavor of it. All right, so let's go back to the case of frequency control elements. So remember, the frequency control element has it's a continuous time element in that the frequency that it changes the DCO by is ideally plus or minus delta I over 2, where delta I is Ki delta, plus some error. And so what it might look like is shown here, the actual FT. And so it's got obviously non-ideal, like non-instantaneous transitions. And also it doesn't go perfectly up to delta I minus delta I over 2 and plus delta I over 2. There's an error in this case denoted as E11I and E00I. Whereas what we really wanted was just this perfect non-return to zero function that when the input is 1, it's delta I over 2, and when the input is 0, it's minus delta I over 2. So if you look at the difference between what we wanted and what we got, it's this red curve. And you can see that when the frequency settles out, we'd like this error to be 0, but it's not 0 because of E00 and E11. And the transitions give us errors. And notice that the transitions depend on whether the last sample was a 1, whether the last input bit was a 1, and let's say the current input bit is 1. If the current input bit is 1, we'll get no transition error if the last input bit was 1, but otherwise we will. So we have error that depends on both the current and the previous input bit. So there are two dominant types of error. There's capacitor mismatches, which gives us these static frequency errors, which I'm calling E00I and E11I, and non-instantaneous transients, which gives us what's called intersymbol interference. The fact that we get a different error depending on whether we go from 0 to 1 or 1 to 0 or 0, 0 or 1, 1, because our error depends on not just the current bit, but the past bit. That is not just the current symbol, but the past symbol. We get what's called intersymbol interference. And it turns out that provided the rise and fall transients are symmetric, which is not usually the case in D to A converters, but it turns out is usually the case in digitally controlled oscillators, then dynamic element matching works on both types of error. Okay, you guys are scarily silent. I doubt I'm being super clear that as
Ian, this is Tom.
Uh-huh.
For me, you're being super clear, and I'm following along. And the fact that you're, explaining DEM at a fundamental level like this, I think it's really good, and I appreciate it because it's something I can remember and I can carry around with me. The basic feeling of how these things work. I'm not sure about our attendees. There may be those very experienced in the digital PLL thing, but the point is that what we're trying to do with these meetings is educate on relevant topics with experienced folks, and you're doing that. And I hope everybody's following along. Again, you raise your hand with the reaction button, and then we'll unmute you.
Okay, I see that Venkata has raised his hand. So thanks, Tom. I appreciate it. Venkata, do you have a question?
Yeah, Tom, I agree, totally agree with you. I think Professor Galton, I think it's very cool, and I'm enjoying every sentence of your talk. Actually, it's to the basic fundamentals. I do have one question. You did mention that the frequency control elements, the fast rate ones, require a fast clock, correct?
Yes.
So that clock itself needs to be accurate, and how is it usually generated? Because we're trying to build a PLL, right? So, and we want a 1 gigahertz clock, and where do we get this from?
So it's actually quite easy. You just divide down the PLL output, and so we will typically just have a divide by 4 or divide by 8 cell. You can also, depending on how you do the multi-modulus divider, you can also use circuitry from within the multi-modulus divider to create a clock. It won't be perfectly uniformly sampled, but it turns out that in many cases that's fine.
Okay, so if we use the output clock of the PLL and divide it, it can be used for this purpose too.
Yeah.
Okay.
And you know, these are very high performance PLLs when you do this sort of thing. So you end up you naturally get a very nice clock.
Yeah. Okay. Got it. Thank you.
Right. You're welcome. Okay. So so recall the conventional solution here. Well, here's the problem, but I'm going to remind you of the conventional solution. Hold on. Oh, I see one other hand. Anurajan?
Hi, Professor Galton. I have a question here about your comment. It seems like the PLL is bootstrapping itself. Something is changing its frequency at the fast rate, and that same change is fed to the fast clock here, like in this slide.
That's true, but the quantization noise is largely at very high frequencies, and so the DCO doesn't generally respond to that. So I'll show you some measured spectra, and you can see.
Okay.
But you know, for example, if F fast is at a gigahertz, right, then your quantization noise is going to peak at 500 megahertz, and you know, even if like what's considered to be a wide bandwidth in PLLs is like a few megahertz, right? So so you've really suppressed this high frequency component.
Got you.
Okay. All right. So this is just a reminder of the conventional solution, and as I mentioned, oversampling the delta sigma modulator solves the too big delta min FCE issue. And DEM prevents the FCE mismatches in ISI from spoiling this by folding high pass quantization noise to low frequencies. And so you could say, well, what can possibly go wrong? And the answer is spectral breathing. And what's particularly annoying about this is it's just not mentioned in, or hasn't until recently been mentioned in the literally hundreds of IEEE papers that are on digital PLLs. And the first digital PLL my group built had the spectral breathing problem because we just figured, well, this is such a well-known technique that there can't be anything wrong with it. And so we built it, and then we saw this phenomenon that I'm going to describe called spectral breathing. It wasn't called spectral breathing then, that's the name we gave to it. And you know, it was extremely frustrating. So anyway, so here is a redrawn diagram of the path from the input to the DCO to the two FCE banks, the integer FCE bank and the fractional FCE bank. Anuranjan, do you have?
Yeah, sorry. Yeah. My question is actually, so if this is such a known problem, like, how come any chip is working with that? Like, why people have avoided mentioning it? Or, I mean, digital PLLs fractional PLLs are there in products, so how come nobody talks about it?
Well, it's a good question. I mean, I know that one of the major cell phone chip companies for one of the major phone companies early on designed a digital PLL for, and I don't want to mention the company names, but you can probably guess who they are. And this was about 8 years ago, and they used it for one iteration, and they went back to analog PLLs specifically because of this problem. There are some things you can do that are simple that partially fix it, and I'll show you that. And I think you know, one of the reasons that digital PLLs you know, are struggling to achieve really high performance in commercial products is because of a number of issues like this. This one's probably the most significant one. So, you know, for clocking and stuff like that, it's you know, if you're not shooting for super high performance, you can often get away with it. But for high performance PLLs, it's tough. And there's a reason why cell phones still use analog PLLs. All right, so anyway, in many PLLs, the short-term variation of D of n is much less than 1. And so when the PLL is locked to a constant frequency, if D of n is wiggling around by less than 1, right, and you're not near an integer boundary, then the integer part is constant and only the fractional part is toggling. And so that means that the mismatch between the FCE banks is not a problem. But if you get near an integer boundary, right, then the integer part toggles as well as the fractional part. And now this mismatch between FCE banks causes excess phase error. And the 1 over F noise and supply and temperature changes cause the DCO center frequency to drift. So eventually D of n gets close to an integer value. So when we built our first PLL, digital PLL, we would dial it in and get a nice spectrum, and then you'd sit back and all of a sudden the phase noise spectrum would sort of swell up as if it's taking a breath of air, and then it would go back down again, just like it was really like the cadence of breathing. It was crazy. And so the phase noise plot intermittently swells up as if the spectrum was taking breaths. It just drove us crazy. So it turns out that a gain mismatch between otherwise ideal integer and fractional FCE banks is enough to cause the spectral breathing problem. So as an example, imagine we have an integer bank and a fractional bank, and suppose the fractional bank is 90% of what it should be in terms of gain, right? Well, now the tuning value is what you wanted minus 0.1 times the fractional part. And the fractional part is a nonlinear, it has a nonlinear relationship to D of n because we've just grabbed the 8 LSBs. And so this nonlinearity is what's causing the problem. And so the FCE capacitor mismatches cause the 2 FCE banks to have different gains. And that means the phase noise swells and contracts erratically over time. Whenever you get near an integer boundary such that the integer part toggles, and that gives us spectral breathing. So here's just a kind of an artist rendition that my grad student drew of the ideal is shown in blue, the ideal spectrum, and these different shades of red and orange are sort of where this thing moves around during these spectral breathing events. And I'll show you some measured examples of this as well shortly. So ways to mitigate spectral breathing. So the simple way to do it it's very practical, but it's only a partial solution as shown here. So here's that same structure, but I've dropped in a digital block called an integer boundary avoider. So let's suppose D of n is toggling near an integer boundary. So let's suppose that we wanted D of n, it's going below 3 and above 3, right? So the integer part would naturally, without the integer boundary avoider, would naturally toggle between 2 and 3, and the fractional part would be somewhere between 0 and 1. So when you add this red and this blue, you get the desired thing. But the problem here is that both the integer part is toggling and the fractional part is toggling. So what we can do with the integer boundary avoider here is we can just rearrange it so that we can make it so that even in this case, the integer part is constant and the fractional part is toggling. So you can see that if you add the red and the blue here, you get the black, just like if you add the red and the blue here. So the integer boundary avoider logic adds 1 to the integer part and minus 1 to the fractional part as needed to minimize the integer FCE bank toggling. So this solves the problem provided the short-term variation of D of n is much less than 1, but it does not solve the problem for phase modulated PLLs. And if you have a lot of drift, every time you cross a new boundary, you'll get one glitch and then it will settle out. So it's not a perfect thing. So I see Julian has his hand up. I think you're on mute, Julian.
Julian, please unmute yourself.
Okay, have I unmuted now?
Yep.
Okay, so just that gain term gives you a discontinuity, right? As you get to the maximum value on the fractional bank, there may be a step up in frequency as you replace the fractional with one integer cell. Am I understanding correctly?
I didn't quite follow. I apologize. Can you hit me with that one more time?
So on the slide before, you were saying there might be a gain of 0.9 on the fractional bank compared to the
This is just an example.
Yeah, but if you take that example, then when all of the bits of the fractional bank are on, and then you make the next step up to being one step of the integer bank instead, then there'll be a discontinuity. You might step much more than one LSB.
Yeah. So if your question is that right? The answer is yes.
Okay, good.
Okay. So, so this solves the problem provided the short-term variation is less than 1, but it doesn't solve the problem for phase modulated PLLs. So a full but impractical solution is to just apply dynamic element matching to everything. And a side effect of that is we would need many more than 8 frequency control elements here. And this DEM encoder now contains a lot of digital, and the whole thing has to be clocked at F fast, which, as I said, is often greater than a gigahertz. So that's not good. And we've got at least 16 integer bank FCEs, and they're all now updating at F fast. We've got a whole bunch of very high-speed lines going into our DCO, which is not good. And so while this in principle works, in practice it's not very practical. So nobody does this, but this would be the ultimate solution if it weren't for these impracticalities. Oh, Hung Ye?
Yes, thank you. About the previous page, I would have a question.
Okay.
Yeah, thank you. In this case, you use an integer boundary avoider, and so that the fractional bank should have some overlay to the integer.
Yeah, you need to expand the range of the delta signal modulator input a little bit. So that's true.
Yeah. So how much of the overlay we would like to have?
I usually just double it. That's more than you need, but it's easy to do. So with simply one more frequency control element, you can easily double the range, and that's plenty.
Okay, thank you very much.
Sure, it's a good observation. Okay, so a full and practical solution. So I gave you a partial and practical solution, and then I gave you a full and impractical solution. So now I'm going to give you the full and practical solution. So it consists of 2 parts. One is to use a new type of dynamic element matching called multirate DEM. And this causes the nonlinearity from all the mismatches across both FCE banks to introduce noise instead of nonlinear distortion. And by the way, green in my slides means good and red means bad. It updates the integer FCE bank at FREF just like before, so that's good. It's low power because most of its logic is clocked at the reference frequency, which, for example, might be 50 or 80 megahertz instead of over a gigahertz. But because we're not clocking the whole thing at the high rate, now we have the mismatches from the integer bank end up giving us a noise PSD that peaks at the reference frequency divided by 2 instead of F fast divided by 2. So it's not sufficiently suppressed by the DCO. So if we stopped at this solution, it wouldn't be a good solution. But we add to that a mismatch noise cancellation technique that dynamically measures and cancels the multi-rate DEM noise, that the portion of it that's not suppressed by the DCO, the low frequency portion. So the multi-rate DEM and M&C together solve the spectral breathing problem. So I've given just an overview of the different ways of solving the problem, and now I'm going to dive into the last in more detail into the MRDEM and MNC approach. So just to remind you, here's our digital PLL. And if we don't address the spectral leakage problem, we have this situation. And so multi-rate DEM will, let me go back a second. So here's our spectral breathing problem. But if we drop multi-rate DEM by itself, what will happen is now we'll just be having a big breath and holding it, right? We'll have all of this excess noise, but it's rock solid. It won't change over time. So it solves the intermittent problem, but it dumps a bunch of noise on top of us. So the noise, it turns out, consists of unknown mismatch-dependent terms multiplied by known pseudorandom sequences, which we actually generate within the multi-rate DEM encoder. And those sequences take on values of 1, -1, or 0 at any given time. And so we know what they are and they're simple, and we can correlate in digital against those pseudorandom sequences, and we can essentially measure this noise and then subtract it out through this separate path here. And so we go from this violet to this yellow curve. So we can essentially put almost all that noise below the noise floor of the PLL. So I'm now going to just talk briefly about multi-rate DEM, and then I'll talk about MNC, and then I'll show some chip results. So this is the conventional solution, and we want to put DEM that will linearize mismatches in the green bank, mismatches in the blue bank, mismatches between those banks, and also associated with the splitting point. And so I claim that if you build this, that will happen. So there's a slow DEM encoder that's running at the FREF rate clock, and I will show you what's inside this box in a minute. The second order delta signal modulator and the fast DEM encoder are the same as before. Here's just a bunch of flip-flops that we retime on the fast clock. And so Ftune is a linear function of D of n, which is what we want because of the multi-rate DEM encoder. And most of the logic is clocked at the slow rate. So these are good things for us. And I don't expect that you can look at this and say, oh yeah, that's obvious. Of course they did it that way. There's a lot of theory and stuff that goes into this, but the point is that the slow rate DEM encoder just consists of simple digital logic. So the whole thing is built this way, where we end up having pseudo-random bits that control the generation of these sequences. So each one of these so-called switching blocks has a switching sequence generator in it, which is this guy, and that's driven by a pseudo-random bit, and it's all just straight up digital logic and not too much of it, and it's all running at the reference frequency. So the mismatch noise cancellation logic addresses the noise introduced by the multi-rate DEM encoder. So the multi-rate DEM encoder gives us linearity in exchange for high-pass shaped error, but the error's PSD peaks at FREF over 2, not F-fast over 2, and therefore it's not sufficiently filtered by the DCO. And the error depends, as I mentioned, on known pseudo-random sequences that we generate within the slow DEM encoder. And so we can use a correction sequence that we can estimate and generate digitally. And the mismatch noise cancellation logic cancels the multi-rate DEM technique's additive error. So it's an LMS, least mean squared like algorithm that computes the coefficients used to generate this extra path E MNC of P, and that's what cancels the high pass shaped error. And excuse me. So the mismatch noise cancellation sequence that we generate, it needs to be added into the DCO. And so we add it at this point, and then we have to make the FCE bank, the fast FCE bank, a little larger to accommodate this extra path. And how much bigger you have to make it depends on how much mismatch noise you have, but it's usually not too much. And then the mismatch noise cancellation logic is here, and it consists of, it's all digital. It consists of a bunch of so-called residue estimators, and each of those residue estimators is shown here. So again, I'm not expecting that in this short talk, you can look at this and say, oh yeah, I see exactly how it works. But I'm trying to convince you that it's practical. And if you're interested in the gory details, you can look at the paper we wrote, and I'm happy to answer any questions too. But anyway, these two paths in each of these residue estimators are designed such that one of them cancels the static gain error. Remember the E11 and E00 error, and the other cancels the intersymbol interference error. So again, this is all sort of straightforward digital logic, and it's what goes inside this MNC logic block. So the timing diagram, conceptually is shown here. So if we disabled MNC and we only had the multi-rate DEM, instead of this ideal frequency tuning curve, we'd have this violet curve, which is obviously way off. But when we introduce this mismatch noise cancellation correction sequence, we get very close to the ideal blue curve. You see the yellow curve here. It's not perfect because this fast clock generated pulse sequence, isn't, it's not a perfect match, but it does quite well in terms of the overall phase noise. So here's some simulation results. The top one shows what happens with just spectral breathing when you have no multi-rate DEM and no mismatch noise cancellation. And then when we turn multi-rate DEM on, but don't turn mismatch noise cancellation on, then we get a deviation. So the dashed curve is what we expected ideally, and our static errors give us this, I don't know, I guess it's reddish, brownish red curve. And if we if we have just ISI, then we have this orange curve. And so when they're both on, you can see that we get very close to our ideal value compared to the case of MNC disabled. So this just shows the convergence rates for the chip I'm about to show you, again simulated, and you can see that the convergence rate is pretty fast. So this is in units of reference periods. So so the convergence is quite fast. It's within just a handful of reference periods for the static, and for the ISI, it converges more slowly and not as accurately. But we don't need it to be super accurate. So I'm now going to transition into talking about the chip. So this is a diagram of the chip described in reference 6. I'm not going to dive into all the stuff in here. You can see here's our DCO and got our integer bank and fractional bank. And we also have some variable capacitance here controlled by an SPI that just sets the band. But the integer and fractional banks are what I showed you before. Got a bunch of place and route digital, and then the analog part, which has a time amplifier in it, a PFD, a dual mode ring oscillator. It sort of plays the role of a charge pump in a conventional analog PLL, or multi-modulus divider. And here we're dividing down by 8 to control the place and route digital logic, and also the fast frequency, the F fast digital logic. So our place and route logic is clocked at F fast, but most of the blocks within it are only clocking at F ref. And so we have a delay chain which gives us our F ref signals. And then we also sample at F fast. So it's just a dive photo. I won't waste time on that. So here's some measured results. Excuse me. So this is the case where everything's disabled, and we're at the point where somebody would press the capture button for ISSEC. So when you go to ISSEC and you look at a digital PLL, or you look at a paper that talks about a digital PLL that's subject to spectral breathing, they show you this plot. This is where we're not near an integer boundary. Okay. However, if you put persistence on and you let this thing just cruise, you can see it's all over the map. We have a 9 dB variation at low frequencies and an 11 dB variation at around 1 megahertz. This is the phase noise plot. And the time here is 2 hours, but this thing will show up in just a few minutes. So it's not like it's a very rare event. You know, usually spectral breathing will occur on the order of once a minute. Anyway, when we turn on our techniques, you can see now we're getting much lower variation. And I think even this 2 dB, I don't think that's spectral leakage, spectral breathing. I think it's actually just variation of the instrument. We recently got a new phase noise analyzer that's much better, and we don't see this anymore. So here are some more measurements. So this is where the multi-rate DEM is enabled. So you can see the big bump here compared to the case where we don't have spectral breathing. But MNC for both static mismatches and ISI is disabled. This shows what happens when we just disable the ISI part. And this is what happens when we have everything on. So this shows the power breakdown for the various different blocks. So you can see that in this case, the ISI wasn't a big problem for us. And so by disabling the ISI portion, we can save a fair amount of power. So anyway, that's what I had to present tonight. So I won't waste time and tell you what I told you. It's just written out here, but I'd be happy to answer any questions that people have. Julian, you're on mute again. I'm still on mute, sorry. There you go.
What's your total power consumption?
That is, give me a second. I got to look it up. It's on the order of 20 milliwatts, but I gotta just remind myself of it. 20
milliwatts in what process?
In 22 nanometer global foundry. An excellent process, by the way.
Oh yeah, no, my digital PLL's in that process too.
Oh, okay, give me 1 second here. I gotta just. I should know it, but we built a few PLLs since then, so they all, after a while, they all blend together.
Well, I think the class of power consumption is probably what Julian's after. I mean, that's 20 milliwatts is for a fair amount of power. Am I right, Julian? Or
well, I guess ours is in the 4 to 6.
Well, what kind of jitter do you get?
Around about the same, the 180 femtosecond range.
Okay, and what?
I need to go back and look at mine now and double check that I don't have spectral breathing. I've got some techniques in there that should get rid of it, but now I'm really gonna have to measure it, aren't I?
Okay. Yeah, give me 1 second. It's not best of class, but it's not that far off either. This is, hold on, sorry, I should have had this on the tip of my tongue, but I was focused on the technique stuff. So looks like our total power consumption was 21 milliwatts. And depending on how we configure this, we can get the jitter down to about 150 femtoseconds. But anyway,
and have you got any idea what percentage of the power is consumed by the spectral breathing prevention?
Oh yeah, that was on this slide. Let me go back. Okay. Okay, so this is the change in power. So basically, it's let's see, we can actually do white shaping, and we can do we can do white DEM, and we can do spectrally shaped DEM. So for white, which actually makes sense to do because MNC fixes everything up. When you enable everything, it's 1.4 milliamps, milliwatts, but you can also let it converge and then freeze the coefficients, and then it's 0.7. And then
that's not so bad.
And then if you choose to, if you don't need the ISI part, then it's 0.83 when you keep everything running, and 0.47 when you don't keep everything running.
Okay, thank you.
Sure. Any other questions?
Yeah, Ian, you alluded to the benefits of digital PLLs, and when you conclude the things like, well, you have a great creative space when you're putting the loop in digital domain, because you're not, subject to, passive circuit constraints.
Mm-hmm.
And so it just seems like there's so many advantages and creativity possible. But I'm wondering, you commented that it may come the time where digital PLLs will exceed the performance of an analog PLL. And I'm just if I heard you right earlier. So my question is something like, what's it going to take? What technology things? Since you mentioned some of these results. Well, these results were on GlobalFoundries 22 FDSOI process. What things in the technology could be done to make that transition?
Well, I don't think it's tremendously technology related. I mean, I think it's just the analog PLLs have been around for longer than most of the people at this talk have been alive, probably. I mean, they've been around for many, many decades, and digital PLLs are have come along more recently. So it just takes time to develop the innovations. And in fact, digital PLLs we're starting to catch up, and then recently there have been a spate of analog PLLs that have been using digital to time converters that have kind of upped the ante and made analog PLLs work better yet again, and digital PLLs are catching up there too. So I think it will happen. I don't think it's really a technology driven so much as innovation driven.
Okay.
I mean, if you can give me better Q and stuff like that, then in my
well, it also seemed like a very low delta C would be interesting.
Yeah, but that's true. But it would have to be really low. I mean, it would have to be like a few attofarads to really be useful. I mean, yeah, the smaller you can make capacitors, the better it will be for me. In that. So one drawback of the FCE approach that I told you about is there's some fixed capacitance that you are kind of stuck with, and that can be a hassle. And so if you gave me smaller realizable capacitors, I could reduce that fixed capacitance. So yeah, that would certainly help, but that's not really the long pole in the tent, I don't think.
The long pole in the tent is this, well, fundamental architectural issue that I see how it is, and then. What else? Well,
so okay, let's go back and look at so here's our architecture that we're using. So we use a time amplifier, which is basically a structure that's made up of inverters that have two states, a fast state and a slow state. And so the faster I can push an edge through an inverter, the better I can make this time amplifier. So that's useful. 1/f noise is really a hassle on these dual mode ring oscillators. And if I could have lower 1/f noise, that would help. And so in fact, one of the reasons that I like 22 FDX so much is that it's got lower 1/f noise than typical FinFET processes, and so it's higher. It's already higher performance in that respect. And if you can keep pushing on 1 over F noise, that would be tremendously helpful. So speed of getting edges through inverters and reduction of 1 over F noise would really be helpful, and reducing the capacitor size, the minimum capacitor size would be helpful.
Okay. Got it. Thank you.
Sure.
Any other questions? Ian, I've been just seeing a fair number of folks that I'm familiar with, and I'm really glad I got a chance to hear your talk, because for me, I can understand why you get the Good Teaching Awards, because I've learned something. So thank you so much for putting in that effort to have your material be absorbable by our members.
Well, my pleasure. Well, thank you.
So I'm going to go ahead and close up the meeting. So if I'll go ahead and take over the screen. There we go. And then let's get the right thing shared. It's getting pretty late in my head. It was a long day. Coming next month, third Wednesday of the month, is Professor Jeffrey Nanzer of Michigan State. Jeffrey's a distinguished lecturer of the MTT Society, and he's going to talk about distributed phased array coordination and just progress on technologies that can address those things. And this is really fascinating. We have beamforming antennas, and then we have, arrays of those antennas. And if you can get phase coherent information, from those antennas, like on the Allen array and other things, you can really do some interesting things, I think. So this could be quite interesting for folks going forward. So just want to remind folks that this talk is brought to you by the Institute of Electrical and Electronics Engineers and the Microwave Theory and Technology Society. And please support us by becoming a member of the IEEE and the Microwave Theory and Technique Society. So thank you very much. Thanks, Professor.
My pleasure. Thank you. All right. Take care.
Bye, everyone.
Bye.